continue, and section 7.5 will continue the story. We last time looked at 7.4. We saw the exercises that went a little bit on complicated side. They are doable, but again, not gonna concentrate on them a lot. I just want to move into the next section because the rest of chapter has its own specific. It's heavy on algebra and on simplifying. And I guess the way to deal with it is to get a piece of paper, pen, and that's what I keep telling you. Write things down, same problems as I do, because if you start doing it yourself, it may not go that smoothly. So you will have a guide how and what be the next step and how to do them. So anyways, there is a pair of formulas here that actually being justified in the statements below. So there is a cosine alpha plus beta, or whatever letters you like. All of a sudden they decided to go alpha beta. So that's cosine cosine minus sine sine. Cosine of both angles minus a product of two sines. And there's another formula here that deals with sine of. Actually, they also have another formula with a difference of these cosines. And turns out the only thing that changes will be the sign. So what I can do, instead of writing this whole thing down, is just change signs. Say if this is a minus, then that sign changes with a plus. And that way we can definitely write this formula faster. So I guess formula for sum of cosines will be one of the key formulas for the future, as well as formula for the sum of sines. That's also another useful one. So it's going to be sine cosine plus sine cosine. So it's a sine times cosine of the other angle, and then plus beta. Again, sine cosine, but now you change, you put beta first and then alpha. So that way is to remember them. So for cosine is cosine cosine minus sine sine. So two cosines, two sines, but for sine they're mixed. And that's actually what happens is in the next pages. So if you wish to actually read justification for this, you can try to do this, but it will take you a little time. So I'll let you do this if you want to, but I guess you don't have to. Again, if you plan to take some calculus classes, that's where we actually do proofs, then you can definitely enjoy this. But again, I'm not requiring to do this. And if someone wants, you can read it, and then next time we can discuss it. Because I like this, a pretty neat little proof here with angles. But you really need to not just read it, but to make sure you have a piece of paper and draw all that yourself. And that way you will see it's pretty straightforward. And then you can see the algebra behind those proofs that deal with distances between points. Of distance formula is used a couple of times here. So it is a little bit tedious. Our goal is to, of course, use these formulas. And here's the one that I just wrote down below. Say, if you have sum, then that's one that I just put down. And if it's a difference, so if sign changes with minus, then this sign also changes with a minus. So they're very similar formulas. Now, where can you use this? For example, they have here a pretty neat pair of identities that you could actually justify using the formula number one, so I can say it's number one for convenience. So if you have cosine of pi over 2, because angles could be any numbers, minus theta, what you're going to end up with a sine of theta, which is pretty interesting. If you draw the unit circle, you're probably going to notice this right away. So angle theta will be less than 90 degrees for convenience. So if I take angle theta someplace here, and then if I also consider pi over 2 minus theta, which is going to be subtracting this theta from pi over 2, so this angle will be, if I take away theta, then I can change the color to red, so we better see it. So this angle will be here like that. Pi over 2 minus theta. Then we can consider value of its cosine. Actually, we're dealing here with a sine, so we can consider value of its sine theta, which is going to be y coordinate of that point. And we can also consider for the angle pi minus theta, value of sine of pi minus theta. So I guess intuitively you could see that indeed looks like you will get the same values, because technically you have this triangle and that triangle that are the same, so sides are the same. So you can see that cosine. Why did I write sine? And I should be careful. See, they changed and now it erases so well, but now it's given me a little bit hard time to get actual things not erased. And that's what happens here. See, whenever they do update, it's not always the best thing to do. So I'm always trying to avoid updates, but it looks like sometimes it's not possible, right? So it's a sign of this. So looks like that the point of this story that this little side is the same as that little side. But they could check it the formula way. So what they do is they say, okay, cosine, cosine. So I need to put cosine pi over 2 times cosine of whatever, theta, minus sine, sine. Again, sine pi over 2 times sine theta. So it's just straightforward plugging in the formula. So now here's my angle pi over 2, right, 90 degrees. So point on the unit circle with coordinates 0 and 1. So cosine is going to be 0 as usual, right, first coordinate, and sine is equal to 1. So, okay, instead of cosine, I put pi over 2. Turns into 0. Instead of sine, I put 1. So it looks like all I have is just the last piece, because it's multiplied by 1, because that one is multiplied by 0, so it disappears. So truly, I guess, pretty neat. So just plug numbers in the formula, and of course use the fact that with pi over 2, you have 0 and 1 for the coordinates of that point. So I think they pulled out these formulas to show you that cosine changes with sine and vice versa. Sine changes with cosine. So I think that's why they put them in the box, because it's kind of exciting. Well, you could also do with other angles, 3 pi over 2 or whatever, and get analogous results. So these formulas are useful. Turns out whenever your angle is not as nice and simple as the others are. Where's the rest of the book? So I think maybe I should reload it, because it takes a little time for it to open. So, oh, it opened. Good. See, it's coming. So they also have formulas for tangent. Maybe I'll look at them next time, because might be too much for today. So I'd like to do more exercises. In fact, I just done one of those exercises here. So we can see when it stays open for a while, then this really takes a little time to get to the next page. So, for example, problem number 11 will enable me to produce expressions for things like 5 pi over 12, because what I need is to decide how we can produce this from fractions with denominators looks like 3 and 4, right? Because we know pi over 3, we know pi over 4, so question is, what can I do with these two in order to get to 5 pi over 12? Well, maybe add them, maybe subtract them, maybe multiply by something. So the question is, what will be in numerators, and do we add or subtract? Well, we can try. The thing is that once you try it a couple of times, you will see it's pretty straightforward, I'm sure. See, all of a sudden it starts erasing my circle, even though I'm erasing here. That's nice update they had for this program. So it just gives me some hard time. But that's good, because I should have some hard time. So if you just add pi over 4 and pi over 3, so you just put 1 and add, then in order to get the same denominator 12, you should have 12s for both. So notice if I do that, if I add them like that, so I get a 3 and 4, it's going to be 7. So that's not what I need, but actually this could be utilized for problem number 13, right? So in other words, if I do problem 13 now, then when they ask me for cosine of 7 pi over 12, I can say this is a cosine of pi over 12 plus, no, pi over 3 plus pi over 4. So pi over 3 plus pi over 4. So this way I can utilize my first formula, cosine cosine minus sine sine, cosine of these two angles, pi over 3, pi over 4, minus sine sine. And the reason I want to always convert this to this pi over 3 and pi over 4 is because I have to utilize things that I know from the unit circle. So I'm going to, I guess, clear this unit circle a little bit. And recall what's pi over 3, pi over 4 in terms of sines and cosines were. And this way we can start, or you could just go to the page before last in the textbook, right? So with pi over 4, that's square root 2 over 2 for both. That's my favorite, right? So pi over 4. It's the same. Sine and cosine are both the same, right? So instead of that one, I put square root 2 over 2, and the same instead of that one, right? Okay, so what about pi over 3? What about the other little angle? Well, it's here. So one of the coordinates is 1/2. That's what I remember. So 1/2 looks like exactly a half here. So the other one, its friend, is square root 3 over 2. X coordinate is cosine. So 1/2 is going here. And the other is y coordinate, that's for the sine. And of course, the negative sign in between. So what do we get? Well, looks like common denominator is 4, and then a square root 2 for the first, and then square root 6 for the second. So what I just did, is I found exact value for this expression. Exact value means you have radicals instead of just placing this in a calculator. I say, so Alex, what about 5 pi over 12? You didn't tell us what it was. Well, besides pi over 4 and pi over 3, we also had pi over 6, remember? So maybe we can try another pair, pi over 4 and pi over 6. Let's see what's going to come out then, right? Remember, another favorite angle, pi over 6. So what if I add these? Well, again, same little arithmetic part. So you need same denominators. Here's 3's and there's 2's. And now we got 5. So it looks like 5 pi over 6 is produced. Oh, 5 pi over 12. Right. See, I'm erasing here, and the disappearance happens with the x-axis. That's what I'm saying. They tried a good update, but when you erase something, it erases at random places. Very nice. So that's why advice is stay away from those updates. If everything works, don't mess. That's actually so-called error 1 in statistics. If you ever take statistics class, that's for testing hypothesis, and that's the worst error that you can make, when everything works fine and you decide to improve, and then after your improvement, things fail. And that's really, why did you waste your time and funds to do that improvement, right? So that's what they just did, updated the Zoom program. Well, anyways, so looks like this will be analogous exercise done for the problem 11, but you're going to use formula, I'll call it number 2, because now they want to sign. So let me do problem 2 here. And that's the specific of this section. All problems are pretty much the same, but these problems require kind of tedious formulas. So advice is have access to these formulas, because nobody wants you to memorize them. Maybe after a while, after a couple of weeks, you will feel better about them, but after that time, you may not need to use them anymore, right? Well, anyways, let us do 11, because that's another formula. So it's a sine of 5 pi over 12 that I split with a sine of, remember what it was? Pi over 4 plus pi over 6, right? We can double check this again if you want to, because I just erased that. So what we do is utilize this sine cosine and sine cosine stuff. So sine first, cosine second, and then vice versa. Sine second, cosine first. So sine cosine, and the same plus here. And then again sine cosine, but now we go with pi over 6 and pi over 4. Okay. So after you do a couple of these exercises, I don't think you have to spend any more time, because you're just going to do same thing again and again, and I think it's a kind of waste of time. And that's why a couple of problems from section should be good enough. So it's a sine of pi over 4. We have pi over 6 and pi over 4. So cosine pi over 4 is radical 2 over 2. We just saw it, right? That's our favorite angle, pi over 4. Now pi over 6. So what happens with pi over 6? Well, 1/2 now will be here, right? So now they switch roles, sine and cosine. So 1/2 will be for the sine, so it'll be here. And then its friend, square root 3 over 2 will be there. So when you add these two, look at the answer you get. Square root 6 plus square root 2. And you say, Alex, this is something that I already had here, right? Well, actually, it was a minus, so it's not the same. So anyways, don't look for any of the resemblance in these. They're just different angles, so there could be various values. So that's one thing. Now, if you move on, you will see that now they use not left side of the formulas, but the right side of the formulas. So they try to complicate things a little by little. So I can do another exercise here, of course, like, for example, problem number 23. So I see sine, cosine, sine, cosine. Say cosine, sine. It doesn't matter. Sine times cosine, cosine times sine. They commute. So in other words, we're working with the second formula, sine, cosine stuff. And since there is a plus, then I'm going to be adding these angles. So it'll be sine of 20 plus 10. Now they decided to switch to those little degrees all of a sudden. Okay, so this is sine of 30 degrees. Well, we just saw what sine of 30 degrees was, right? It was here. Sine of pi over 6, which is same as 30 degrees. You still remember that? Because what we have is 30 degrees, 45, and then 60 is pi over 3. So 30 degrees is 1/2. You see, you could just put this in a calculator and get this. Yeah, 1/2, 0.5, but again, exact value. So if you get square root 3 over 2, then it's going to be decimal, not exact, but approximate. So I guess the point of this next group is to recognize those two formulas. They also have tangents, but next time I will show you those. So that's pretty much all it is. Now they return back to all these quadrants stories. So I can do one more, and I think that should be enough with this, because we will return to these formulas in the next sections because they underline something important. And that's why I want you to see these formulas. I know they're tedious. I guess that's the most tedious part of the course, because here we utilize long formulas. But a good thing about formulas is all you do is just plug numbers in, and that's it. So if you have a formula in front of you, problem is done. You just replace whatever variables with numbers, and you finished. So here's the sign they gave us, 3/5. Now they also say that cosine of beta, write it here, problem, I have to work with it, is equal to 2 roots of 5 over 5. Okay. Sine alpha, cosine beta are given. They also give us quadrants here. So why is it so important? Well, because we can get the plus or minus for the other value. Like if you have sine alpha, which is 3/5, so it's here, then you have two angles, possibly. You see, one can be less than 90 degrees and the other greater. So if they told us that alpha is in between 0 and pi over 2, we're here. So our cosine is positive, because otherwise cosine will be negative. So cosine here will be with a plus sign. That's cosine alpha. So I put plus, so I don't forget. Plus what? Well, there was a formula that we utilized all the time. Sine squared plus cosine squared, whether it's alpha or beta, doesn't matter, was equal to 1. So from here, I can pull out cosine from this formula. So what's the cosine? Write it here so we have room. Cosine of alpha will be a square root from 1 minus sine squared, right? Using this Pythagorean identity. And analogously for the other one, if I want to get a sine beta, then it'd be a square root from 1 minus cosine. So basically that underlined formula does it all. But again, I have to figure out if it's with a plus or with a minus. So for the second guy, we have, look at this, quadrant number 4. So our beta, somebody sent me homework that makes me happy. I love this sound. So we got a cosine, which is positive now, some kind of number here. But the angle is here, angle beta, because we got that quadrant number 4, right? So for beta, I put a minus. That way I would not forget minus. So they give you these quadrants in order to make sure you put the right sign with this. So now I'm going to get the answer. So for the cosine of alpha with a positive, I'm going to get the fractions 1 minus sine squared. So from 1, I have to subtract the square of 3/5. Whatever it's going to be, we'll find out. So this is going to be 25ths. So I'm going to have 25 25ths minus 9 25ths. 25 minus 9 is 16 25ths. So when I square root 16, I get 4/5. But this is nice. So with a plus. Now with beta, it's going to be a little bit messier because now we're going to subtract from 1 cosine squared, and this is what I'm going to have to square. Okay, so I'll put it with square. 2 roots of 5/5. And then when we square this, then our denominator will be 25. So I can, again, put 25 25ths instead of 1. And we're going to be subtracting some 25ths. How many? Well, 5 squared is, the root of 5 disappears, so just 5. And 2 squared is 4. So 4 times 5 is 20. Okay. So we end up with a square root of 4 over, oh, sorry, 5 over 25. One can say, Alex, this is just 1/5. But nowadays they like to have no square roots in denominators. So I'm not going to cancel. I'm going to just leave it like that. And that's not it, because it's only start. Because what they want is parts A, B, C, and so forth. So that'd be actually 4 answers for this exercise. Maybe I'll do just one, so you can do another one. And that'd be, I think, a good idea if you can try. I don't think I'm going to ask you this for a quiz. I know some people will panic and shut down, so I don't want that to happen. I'll just rather do it myself. So what they want is like part A for this exercise. I'm still in exercise 33, by the way. So what they say is find sine alpha plus beta. Okay. Notice they didn't give you the actual angles. They just gave you what sines and cosines are. But that's fine, because what I'm going to do is use formula number 2, right? I already know it's sine, cosine. So sine first, cosine second. It's always first, second. And then plus, again, sine, cosine, but then they switch their roles. So it'll be sine beta, cosine alpha. Or you can switch them with cosine alpha, sine beta, but then it's kind of getting a little bit involved with memorizing. So instead of sine alpha, I already know 3/5. In fact, I already know all of them because we just calculated them. So I also know cosine alpha. We just calculated it. It's coming here. Cosine alpha was 4/5. Put it here. And with beta, we also have both numbers. So the rest of problem is standard. So instead of, and cosine was positive. Now with beta, assumption was negative, right? So they gave us that cosine beta was positive, so that was nice, 2 roots of 5 over 5. But then for the sine beta, we had a minus, right? So I had to put minus here and minus there because it looks like I forgot almost. So it'd be negative root of 5 over 5. Super. So it looks like my denominators are same. So they both 25. So 3 times 2 is 6 roots of 5 minus 4 of these roots of 5. So I can subtract and get 2 square roots of 5 divided by 25. This is my answer. Again, with radicals, that's why they have this question about exact values. But notice you have formula, you plug things in, and that's pretty much all that is happening. So again, that's why I'm saying you should do one problem without a hurry, and this way it'd be good enough. So I think I'll do another exercise instead of giving you any quizzes. So I'm gonna do exercise that says establish identity. Look at this. More problems that came from previous section. Remember, last time we had some fun with complicated looking exercises that we had to produce from left side, the right side, or from right side, the left side. Or if it gets real involved, then you work on one side and then you work on the other side and then see if you can make them be equal, what you should do. And the key part of all these exercises is to keep track what your goal is, because you might get carried away with in totally different direction, because it all depends on them, what they ask. So, for example, let me get a problem without tangents. I don't want to tangents today, it'd be too much. So they have anything without the tangents below these, because first group is pretty straightforward. All you do is just plug into either this or that formula and you get the answers. It's not interesting. What about actual identities? I'm trying to see if something is here without tangents or cotangents. Oh, here's the one, number 69 exercise, the one that has a product of 2 of these. How would you like that? Number 69 exercise, I definitely want to work with the left side, because there we right away gonna apply formula number 2 twice. And our goal will be to produce what's on the right side. So whatever it is on the right, I need to produce. So sine alpha minus beta. So I'm gonna write it sine alpha cosine beta minus sine beta cosine beta. I said beta and put alpha. That's not good idea. Cosine alpha. I'm afraid to use this eraser because when I start using it, it just kills everything. See, I'm erasing here and it just disappeared in the other place. That's definitely no good. Well, anyways, sine beta cosine alpha. So I better write it correctly from very beginning. And that's minus, so I put minus here. Even though it doesn't really matter because you see first is minus, the other is plus, but just to be consistent, okay, I put minus. That's my first thing. I'm afraid to use eraser now because this is definitely no good. So now I have to multiply this by exact same, but with a plus. So again, sine alpha cosine beta plus sine beta cosine alpha. And then I have to multiply these. So multiplying as usual, like FOIL method. This one times that one, right? So multiply sine by sine, it's a sine squared. Then cosine by cosine, that's cosine squared. Okay, we'll start. Now I multiply sine. So now I'm going to have four-term product. Sine alpha cosine beta multiplied by sine beta cosine alpha. How would you like? All of them are here. So now it's time to multiply by the second term. And notice that with a minus sign, will be again sine beta cosine alpha. So they will cancel, in other words, I think. Let's check. Sine beta cosine alpha. Actually, not really. It'll be squared and it'll be squared. Okay, but what about the last? So wait a second, multiply sine by sine and cosine by cosine. I think I multiplied the last ones here, and then I'm gonna get these ones that cancel. I'll put it underneath, so it's a cosine beta. I think you should get a piece of paper and actually write it down, because otherwise it's really kind of questionable. So cosine beta. So the point of the story that these terms here is cosine beta, cosine beta. There's sine alpha, cosine alpha, cosine alpha. And the one that is not underlined supposed to be here. I put too many cosines. Let me check this out. Sine, cosine. So first was sine beta. It's sine. Okay. So it's so easy, just one thing and you messed up. So sine beta cosine alpha. Why do I know that they messed up? Because these things, they have to cancel, because our goal is here, two terms. And the third term is not going to be possible. So the point is they all disappeared. And that's what happened. So first was sine beta, right? Sine beta, cosine beta, and there is a sine alpha and cosine alpha. So sine alpha, there's sine alpha, sine, that's a beta. So this way, we ended up with that difference. So now what we do with that difference? Well, looks like we can factor out, since it's a sum minus difference, actually what we have here for the end, sine squared minus sine squared. And now we have sine squared cosine minus sine squared cosine, but now they're in the switch positions. So what should we do? That's interesting, right? Sine squared alpha. Do we have something to factor out? Not really. So I have the only formula to work on. See, now at this stage, something interesting happened. We got kind of stuck, but not really, because since I can't factor anything out, notice here's sine alpha, but there is a sine beta. Here's a cosine beta, but there is a cosine alpha. So I need to somehow break it out to, instead of sine, put cosine, or instead of cosine, put sine. So it looks like in this case, I should put, instead of cosine, sine, because at my end result, I don't have any cosines. So instead of cosine squared, I can just get a 1 minus sine squared, right? So instead of cosine squared beta, I guess I'm going to need a little bit of room here. So instead of cosine beta, I'm going to use, let me go green with the old stuff so we don't mess it up. So sine squared alpha. See, these problems, they get involved. And then instead of cosine squared, I'm going to put 1 minus sine squared. So I'm going to use red so we can better see this. So it's 1 minus sine squared. Now it was beta, so I want to keep track. It's a beta. Okay, so that stuff was canceled. And the last piece. So same thing I'll do with cosine in the last piece as well. So it looks like this minus sine squared will stay, right? This piece will stay. Instead of cosine squared, I put 1 minus sine squared. So that way I get no more of these cosines, because again, my goal is to get pair of sines. So you always need to check and see what your end result has to be. So it's 1 minus sine squared. Okay, and now I'm gonna see what this is gonna do for me. So sine squared, you multiply by 1. That's my favorite. It's same sine squared. Minus, now we have sine squared alpha, sine squared beta. Okay. Now for the beta, I also distribute. So now multiply negative by that and negative by that. So I'm going to have to change signs. So sine squared beta times 1. And then negative times negative is positive. Sine squared beta. And then sine squared alpha. You see what happens? These two guys cancel. Right? And we ended up with exactly what we needed. Sine squared alpha minus sine squared beta. So once again, the goal of all these little formula exercises always the same. Look at what your goal is and try to get closer to it. And that's why here at this stage, I think this is an awesome example to illustrate it. I got rid of those cosine squares by turning them into sine squared, because our goal was only sines. Because they could have asked to get cosines. You could also write this same thing with cosines. So you would have utilized the same formula the other way around. But that Pythagorean identity, sine squared plus cosine squared is 1, is probably the most useful formula in trigonometry. In every other exercise, you end up touching it. So I think that'd be good enough for today. I think we already had plenty of things